Hello everybody and welcome back to Statistics with Professor Val Lachman at Frederick Community College. In this video I will discuss the Central Limit Theorem, which is a big concept, a very important topic in our class. So we will develop the whole idea of the distribution of the sample mean and talk about the theorem itself and then solve some application problems using a graphing calculator. So before we get into computations, I'd like to develop this idea of the distribution of the sample mean by looking at the experiment that we've done in class before. So imagine you have a pair of distinct dice, and we're going to go ahead and roll the dice and look at the sum of two numbers. So if we get 1 and 1, then the sum is 2. Or we could get 1 and 5, then the sum is 6, and so forth. So all your possible outcomes are listed right here, and the smallest number is 2, the largest number is 12, and then everything in between can happen, okay? And of course there is a probability associated with each one of these outcomes, so we could come up with a whole table that describes the probability density function. Okay, now let's see. Let's go ahead and simulate this. So I'm going to use my calculator, and if you have your calculator, you should do the same thing. Okay, we're going to go to Math, scroll to Probability, and we're going to select 5. That's our random integer function, and we need to tell the calculator what's the smallest value we allow. That's 2. The largest value we allow is 12. Okay, that represents these possible outcomes. And we want to simulate rolling the two dice 20 times. So we're going to say 20, close the parentheses, press enter. Okay, so these numbers, the sequence of numbers, represents what? The experiment of rolling the dice 20 times. Okay, I'm going to store my numbers in L1. Okay, and now I would like to take a look at the mean sum of this experiment. So I'm going to go to one variable statistics and just compute the mean. Okay, so I got 8.4. This represents the average sum if I were to roll the two dice 20 times. Okay, now let's go ahead and do it again. So I'm going to go back to probability, function 5, 2, 12, 20. Okay, I generate another sequence, and I'm going to store this in L2. And also take a look at the mean of this sequence of numbers. Yep. Place. So I'm going to go ahead and take a look at one variable statistics, now L2. Okay. And now my mean is 5.4. That tells me what? Okay, so in this experiment, when I rolled the dice 20 times, again, looks like I got a lot of low values, right? Before that, I got some high values. My mean was 8 point something, right? Let's go ahead and just do it one more time just to develop this idea of what exactly is it that we're doing here. Okay, so let's generate another sequence, 2, 12, 20. Okay. I'm going to store these numbers in L3. Okay, now if you go back here, you'll see all of my sequences. So here's my first sequence. Looks like there's a lot of high values here, a bunch of 12s and 10s. Okay, this is my second sequence of numbers. Here's my third sequence. There's 11, 8, 8, 11, and so forth. Okay, let's compute the mean of that one. Okay, so one variable statistics of L3. Now my mean is 6.45. Okay, so notice anytime you do this, of course, if you're doing it with me, your numbers will be different. But your mean is concentrating right around here, okay? You don't get a mean of close to 12 or 2. You get something that's kind of in the middle of this sequence of numbers, right? And it makes sense because it is more likely to get numbers that are between 5 and 9 than something that's over here. Now, of course, you could get it, but not as often as these values right here. So what we've just demonstrated is part of the distribution of the sample mean. Okay, so let's go ahead and go to the next slide. Okay, imagine we all have done this simulation many times and came up with every possibility of 20 rows and then computed all means. Okay, this would describe the distribution of the sample mean. Okay, because the sample mean varies each time, as you've seen with me just demonstrating it 3 times. All 3 times we got a different mean. It is a random variable with the probability distribution that's called the sampling distribution. So we're no longer looking at x as the random variable. We're going to be looking at x bar, the mean. Now the mean is the random variable. And mean of the sampling distribution, the notation looks like this. So you have your mu, your standard Greek letter, with x bar over here. Okay, and the important difference is that the standard deviation of the sampling distribution, the name for it is standard error, and now it's computed by taking the population standard deviation and dividing that by the square root of n. Okay, this is a very important distinction that we will need to keep in mind as we go with our computations. Okay, so let's take a look at our pictorial representation of what we've done. Let's say you have a huge population of a finite size, but really big, okay? And you take all of these samples of the same size, just like we've done with 20 rows. Same size, okay? 1, 2, 3, 4, finitely many, but many of the samples. And each sample produces a different sample mean. Okay, so now take every possible sample of size n and record the sample mean. This is the distribution of x bar. Okay, so we could think about it as, okay, all of these observations. What is the spread? What is the center, okay, of this distribution? All right, and it might take you some time to kind of wrap your head around it. What does it actually mean? The distribution of the sample mean, okay, not just variable x, but x bar, okay? So the central limit theorem tells us something incredible. There is a formal statement, a formal, rigorous mathematical statement for central limit theorem. We will not discuss it in this class. I'm just going to tell you what it says in simple words. It basically says the following. If we have a population with known standard deviation and the mean, okay, so we have some parameters, population mean and population standard deviation, and we take a sample size that's large enough, okay, which means 30 or bigger, then the distribution of the sample mean is normal, regardless of what the population is, okay? The distribution of the sample mean, so this notation here says the sampling mean is distributed normally, and these are your parameters, okay? The mean is the same as the population mean, but here the spread, this quantity right here describes the spread. This is what we call the standard error, and it's computed by taking the standard deviation and dividing it by the square root of n. Okay, so that's what we will use in our computations. And now I have an example that's worked out for you. So what I want you guys to do, actually fill in all of the steps as I'm about to, including calculator commands. Okay, let's take a look at this example. The EPA rates the mean highway gas mileage of the 2011 Ford Edge to be 27 miles per gallon. Assume the standard deviation is 3 miles per gallon, and we have a rental car company that buys 60 of these cars. Okay, so let's think about what's happening here. We have a population of cars with a known mean 27 miles per gallon and a standard deviation of 3. We have a sample of 60 cars. Now notice nowhere in this problem does it say that we have a normally distributed random variable. That's actually not needed because we have a sample that's large enough. So we want to answer all of these questions. Okay, so over here I have this set up for you. Let's see, we have the mean of 27, standard deviation 3, sample size is 60. Okay, the first one is asking what is the probability that the average mileage of the fleet is greater than 26.5. We can use the normal distribution to model this because we know the sample mean is normally distributed. So the first problem says compute the probability of the mean being greater than 26.5. Okay, that's normal CDF. Greater than 26.5, so 26.5. And then we do 1E99, right? That's our upper limit, which is infinity. What is the mean? Mean is the same, 27. But what about the standard error? Okay, this is the part that I really want you to focus on. It is not 3. It is 3 divided by square root of 60. Okay, our spread is no longer 3. Our spread is actually a lot smaller. It is 3 divided by root 60, and that's what we're going to plug in into our calculator. Okay, so let's go to our calculator. We're going to go to second variables, normal CDF. Okay, 26.5. We go to infinity. Okay, 27 is the mean, and standard deviation is 3 divided by square root of 60. Okay, so the probability here is what? 0.9016. Okay. All right. Next part. What does the next part say? What is the probability that the average mileage of the fleet is between 26 and 26.8 miles per gallon? Okay, we've done problems like that before with regular normal, right? But now we have 26. What was the other one? Let's get rid of this stuff. Okay, 26. 26.8, so that's low limit, high limit. The mean and the standard deviations are just like the ones above, so I'm just going to copy it here. Mean and standard error. Okay, let's go ahead and compute this. Second variables, normal CDF, we go from 26 to 26.8. 27 is the mean, and then 3 divided by square root of 60. 60, not 600, that would be very different. Okay, so our probability here is 0.2979. Okay, 90th percentile. Okay, this would represent what? Compute and interpret the 90th percentile of the average mileage of the fleet. fleet. Okay, remember, percentiles are computed which way? They're computed using the inverse normal. Inverse normal command. Okay, area to the left is 90% or 0.9 as far as the probability goes. The mean is 27. Standard error is 3 over root 60. Okay, and we will talk about the interpretation of what this actually means, right? So let's go ahead and compute this. So this is going to be second variables. Inverse normal is function 3, 0.90, 27, 3 over root 60. Okay. 27 what? Let's see. 27.5. Let's go with that. Okay. 27.5 of what? Miles per gallon. Okay. What does this actually mean? Interpretation. Okay. The top 90% of all samples of 60 cars of this type cars will have the average of what? 27. Will have the average mileage, right? Or gas economy. Okay, 27.5 miles per gallon. Okay, that's your interpretation. All right. So this is going to be what? Okay, the higher value, right? So the top 90% of the samples of 60 cars will have the average of 27.5 miles per gallon for your gas economy. Okay. Would it be unusual if the average mileage of the fleet were less than 26 miles per gallon? Okay. When it's asking us something about unusual, we need to compute probability. So this is asking if the probability is small, right? So what do we do here? Normal CDF. Okay, we go from negative infinity now. That's our low bound. To 26. The mean is 27. And the standard error is the same. Okay, so think about it this way. Would it be unusual if I collected a sample of 60 cars and computed the mean of that sample, and that value is less than 26? That's what it's asking. So let's go ahead and see. Okay, second variables, normal CDF. We go from negative infinity up to 26. Mean is 27. Standard error is 3 over root of 60, which is actually small. We have a very small spread for this distribution. Okay, so we get 0.0049. The answer is yes. Unusual, because the probability is less than 0.05. Okay, this value is small, right? Let's highlight it. Okay, this is less than 5% chance happening, so this is definitely unusual. Now let's take a look at the last problem. Would it be unusual for just one car to have gas mileage less than 26 miles per gallon? And what assumptions should we have to answer this question? Well, if we want to use the normal distribution, then we must assume that all MPG is normally distributed. So let's do the computation first. Normal CDF. Okay, where are we going from? From negative infinity to 26. The mean is 27, but now we're talking about one observation. So we're not talking about sample mean anymore. We're talking about one observation. One way to think about it is, okay, one is just a very small sample of 1. Okay, well, root 1 is just 1, so you just have your standard deviation of 3 instead of standard error of 3 over root 60. Okay, and we must assume normality here. We must assume normality for MPG. Okay, not the average. We know the average is normally distributed, but what about the MPG itself? Okay, so that's the assumption that we need to have, and let's go ahead and compute this. I'm just going to do second enter, and here the only thing that I need to change is my standard deviation. So I'm just going to get rid of these values here. All right. So let's see. We go from negative infinity to 26. Mean is 27. Standard deviation is 3. Okay, 36.94. Okay, that's your probability here. 0.3694. Not unusual at all. Okay, do you guys see how these are different? Okay, they're asking two different questions. The first one saying, is it unusual for the entire sample to have a sample mean lower than 26? And yes, this is the probability. It's so small. What about just one car? Would it be unusual for just one car to be lower than 26? Not so much. Okay, pretty high chance actually. Okay, so I wanted you to see this difference. Okay, and just really think about what it means when we talk about a random variable versus the sampling. Okay, the distribution of the sampling mean. Okay, very different concept. So make sure when you guys solve these problems, use the correct standard error. This is number one thing that we need to remember when we're talking about the central limit theorem computation. So let me highlight these. This is very, very important. Okay, so standard error, a lot smaller than standard deviation. Okay, very different computations. So that's problem 1. Let's go ahead and take a look at the next problem. Here we have high school boys that high school boy mile runs are normally distributed. That's given to us with a mean of 6.7 minutes and a standard deviation of 1.2 minutes. Which times separate the highest 20% of the means, and what are the lowest 80% from the lowest? Okay, let's take a look. What does it actually say? Which time separates the highest 20% of the means of the run times in the sampling distribution of sample size 6 from the lowest 80? Okay, so we're looking at a sample of 36 times. Okay, so let me see what I have prepped for you. Okay, we have a sample of 36 where the mean is 6.7 and the standard deviation is 1.2. So it's asking us to find the time that separates the highest 20% from the lowest 80. Okay, so what does it mean? We need to compute. We need to compute percentiles, right? Percentiles means inverse normal. So what do we do? Inverse normal. Okay, 0.80. And let's see, the mean is 6.7 and the standard deviation is 1.2, but we're talking about the average time, so we need to divide this by root 36. Okay, this will be the time that separates the top 20 times from the bottom 80, right? Now in this case, higher times are not desirable, right? So when boys run a mile, okay, they want to run it fast, not long. So those are the top 20% that are probably not desirable. Let's go ahead and compute this. Okay, so second variables, inverse normal. We have 0.8. 6.7, and then standard error is 1.2. Divide by root 36. We can just compute that. That's 6. Okay. Oh, I'm doing completely different function. I apologize. We need to do inverse normal. Okay. 0.8, 6.7, and 1.2 divide by 6. Okay. 0.8 is the cutoff that we want, right? Okay. 6.7 and 1.2 over 6. Okay, good. So we get minutes, right? 6.87 over minute. 6.87 minutes. Okay, so what does it mean? Times that are 6.87 minutes or longer are in the top 20% of all times. Okay, this is for a sample of 36. Okay. All right. That's our computation and interpretation. So remember, when you ask to compute percentile, that's the inverse normal function. Okay. And let's see, let's do one more problem and we should be done with this part of the lecture. We have a normal distribution of homework assignments per year, has a mean of 80 and a standard deviation of 16. Now in this case, this word normal doesn't actually mean normal in the statistical meaning. Okay, so this is just a word. Okay. And we need to answer the following question. How many assignments separate the lowest 25% in a sampling distribution of 32 samples? Okay, so we want to find the lowest 25%. Now, in this case, our variable is actually discrete number of homework assignments. This is not a continuous variable, but that's okay. Sometimes we could use a continuous distribution to approximate values for discrete random variables. Okay, so we're not going to get into details, what assumptions you need to satisfy, but let's say everything is okay and we can apply normal distribution here. Do we have a sample size that's big enough? Yes, 32 is bigger than 30. Okay, remember your assumption for normal, you need to have, or for central limit theorem, that sample size is bigger than 30. Okay. So normal distribution for homework assignments per year has a mean of 80, standard deviation 16. How many assignments separate the lowest 25%? Okay, so let's see, mean is 80, sigma is 16, sample size is 32. So once again, this is inverse normal function. Okay, we're going to do 0.25, mean is 80, standard error, okay, that would be 16 divided by root of 32. Not a perfect square, so we would just plug that in just like that in your calculator. Okay, second variables, inverse normal, 0.25, 80 for the mean, standard deviation, standard error is 16 divided by square root of 32. Okay, so that would be 78, right? 78.09, we want to round it to the next number, so 78 assignments. So let's just go ahead and go back to the statement of the theorem and just reiterate what it's asking, or what it's telling us. It's saying the following. If you have a population with known parameters, mean and standard deviation, Then, if you take a sample large enough, 30 or bigger, the distribution of the sampling mean is normal, regardless of what the distribution of the population is. Okay? And we say that the mean, the sampling mean, is distributed normally, and these are your parameters. So the standard error, that's what we need to compute every time. Okay? And be very, very careful. Do not use just the standard deviation, but use the standard error, which is the standard deviation divided by the square root of n. In the next video, I will discuss the central limit theorem for the sum. Thank you for watching.